So today we're going to cover 5.4, which is the indefinite integral. So 5.4, the indefinite integral. Okay. So the indefinite integral is basically something that you already know how to do. In the previous sections, you learned how to do the definite integral, which had limits of integration and found area under the curve. The indefinite integral is just a new type of notation that deals with the antiderivative and strictly the antiderivative, and it does not have a lower or upper limit of integration. Okay. And all it really means is when you see this symbol, this means find the derivative. Okay. So this integral sign just means find the derivative. Okay. So this means find the derivative. I mean, basically, that's what it's saying. Okay. So we already know that when you take the integral of f of x dx equals, we know that when somebody asks you to find the, oops, I'm sorry, it's not find the derivative, it means find the antiderivative. Sorry about that. I was worried about how to spell it, and I ended up spelling the wrong word. Antiderivative. Okay, find the antiderivative. Okay, so we already did antiderivatives in previous sections. So all this is now saying is, now that you know how to do the antiderivative, let's use this new notation, the integral f of x dx. So that's what this is right here. This is saying the indefinite integral of f of x dx, which means just find the definite integral. And we know that's big F of x plus c, where f prime, big F prime of x is equal to f of x. So remember I talked about this, that whenever you wanted to see if your antiderivative was correct, you could always take the derivative of it. And if you get back to where you started, if you get back to the integrand, then you know that you found the correct antiderivative. So let's try a little practice with this. So if we have the integral, we have the integral of 3x plus 2 dx, and remember this dx is necessary, you have to write this. Okay, so if we have the integral of 3x plus 2, now I'm going to write it out the long way, but in reality many of you will start skipping this step. This is actually the integral of 3x dx plus 2, oops, sorry, plus the integral of 2 dx, but that's really the integral of x dx plus 2 integral dx. And we know that the antiderivative of x is x squared over 2. So this is going to become 3x squared over 2. And this will become plus 2x because the antiderivative of dx is just x. So this is just going to become 2x plus c. And that would be our answer. And we're done. Okay, and that's all there is to it. That's all the symbol means. So technically, you've already done this section in 4.9, or depending on the book you're using, with the antiderivative section. Now we're just moving this on to the notation for the antiderivative. So right now, these are kind of our core. We can't do every single function and the antiderivative of it. So for now, we're going to kind of stick to ones that we know how to do. But as we progress further in Calculus 1, and then when you take Calculus 2, you'll learn other functions and how to deal with combinations and compositions and much more difficult functions. So let's look at another example. Okay, so this one says, find the antiderivative of, oops, not find. Find the antiderivative of the integral of sine 2x all over cosine x dx. Okay, now the thing is you guys should take this back to your old school trigonometry. You guys know all your trig. You know that the sine of 2x is equal to 2 sine x cosine x. So you have your double angle if you need it. You have that the sine squared of x plus the cosine squared of x is equal to 1 if you need it. You have tan squared x plus 1 is equal to secant squared x, once again, if you need it. And you have 1 plus cotan squared x equals cosecant squared x. So these are all trig formulas that you have. You also have the double angle for cosine, which is cosine 2x. I forgot to write that one, but I guess I could add that. Cosine 2x is worth cosine squared x minus sine squared x, and then you can do a bunch of variations of that. Maybe I should look that up after this to make sure I memorize that right, but sometimes I don't use that one as often, so sometimes I even forget that one. Okay, so now we can use these trig identities to help us with a problem like this. Now, hopefully you guys understand that this is a problem because this is a division problem and we don't know how to do integration or antiderivatives of division. So what we're going to do is we're going to rewrite it as the integral of 2 sine x cosine x using the double angle over cosine x dx. We can clean up a little, right? Those will cancel and become 1. And we end up with the integral of sine x dx. And remember, all I'm doing is I'm taking this constant out. That's allowed with derivatives. You're allowed to move constants and then take the derivative of the function and then, you know, kind of think of the constant as reappearing or multiplying or dividing, whatever the case may be. In this case, I'm moving the constant to the front of the antiderivative, or I'm pulling it out of the integral. This is okay as long as it's a constant. You normally do not even attempt this with variables. Sometimes there's some weird stuff you can do, but in general, you never want to take out a variable from a integral. You always kind of want to stick to constants only. And you can't pull addition or subtraction out of constants. You can only pull multiplication or division out of integrals. So this is something you want to kind of focus on. And I do it all the time. Even sometimes leaving it inside might even make the problem easier. I just have a habit of pulling the constant out. So now we end up with the 2 times, what was the antiderivative of sine x? Well, it has to be negative cosine x plus c. So this would be negative 2 cosine x plus c. And that would be our answer. Okay. So now that we, and again, you guys should have been practicing this, you know, quite a bit from earlier sections. So now let's look at absolute values. So absolute values take on are a little bit more difficult. You have to be a little bit careful. So suppose we are given that v of t is equal, or I'm sorry, v of t is the velocity, function. We have the following. We have that the integral from a to b of v of t dt. So this is now a definite integral. We're switching back to definite integrals. Gives displacement of an object. Why did I write it like that? Of an object from t equals a to t equals b. Okay. Then we also know that the absolute value, the absolute value of v of t dt gives the distance. So this one is displacement, this one is distance, the object traveled from t equals a to t equals b. Okay. So, and you guys remember that displacement is, let's say you walk to the right 10 feet, but then you walk back from the same direction you came another 10 feet. So your displacement is actually 0. because you're back to where you started. However, distance would say, well, if you walk to the right 10 feet and then you walk back 10 feet, well, you walked a distance of 20 feet. Okay, so distance, absolute value, is to account for the fact that sometimes you might think of walking back to where you came from a negative distance, even though it's hard to talk about negative distance. So the absolute value guarantees that every piece of distance, whether it's left, right, up, down, we're measuring those distances. Okay, so we could do something like this. This idea could lead us to, oh, and by the way, this is the velocity function. And remember, from derivatives, you get the velocity function by differentiating the position function, s of t. So if you take s of t and you differentiate that, you would get v of t. Well, then how would you take v of t and get back to the position function? Well, you would take the antiderivative. So that's what we're doing here, is we're taking the antiderivative of the velocity functions, and that is giving us back the position function, whether it's distance or displacement. Okay, so for this one, we have from -1 to 3 of the absolute value of x minus 2. And kind of a rule of thumb, to be honest with you, in calculus is pretty much anything to do with absolute values in calculus, I've noticed, just seems harder. Okay, whether it's derivatives, whether it's integrals, whether it's limits, you just have a little bit more work to do and you have to be careful. And hopefully you guys remember that there was a way to write absolute values from the derivative. When we worked with derivatives, we could write absolute values in terms of a piecewise function, and we also did it with limits, I believe. So we could take the absolute value of x minus 2, and the absolute value of x minus 2 is equivalent to negative x minus 2 for x less than or equal to 2, and x minus 2 for x greater than or equal to 2. So this is how, so the breaking point is 2. Remember, so when x is less than or equal to 2, we get a negative. And then when x is greater than or equal to 2, we get a positive. And when it's 2, it's 0. I guess we could just call it greater than or less than, but we want this to be a function. So now we can find the derivative of this. I'm sorry, not the derivative. We could rewrite this. We could rewrite this as two separate integrals. So what you could do is you could think about this as the first integral, and you could think about this as the second integral. So what I'm going to do is I'm going to say the integral from -1 to 2, right? Because 2 is the breaking point. I'm getting that from right here. Okay, 2 is the magic number for this absolute value. So we're going to go from -1 to 2. And which one of these graphs would deal with from -1 to 2? Well, that would be, this is less than 2, so or equal to 2. So this would be from -1 to 2. So we're going to say negative x minus 2 dx. And then we learned with properties of definite integrals, you could then start this one from 2 and have it end at 3, and we would cover the entire interval. So this would be from, x minus 2 dx. Okay, so now I kind of ran out of room, so I'm going to come way down here. And we're going to say that this is going to become negative, and then the integral, the antiderivative of x is x squared over 2 minus 2x, and this is going to be from -1 to 2 plus the integral of x squared over 2 minus 2x from 2 to 3. So I did my definite integral. Okay. And now let's see what we get. So we should get negative, and then this will be 4 over 2 minus 4. And then it would be plus, because this minus right here would become plus. And then this would become 1 over 2 plus 2. This will become plus 9 over 2 minus 6 minus 4 over 2 minus 4. When you add all of this up, you should get 5, okay? So this would be our final answer. When you plug all this in your calculator, you just clean it up, you should get 5, okay? So this is the kind of the main way that we should deal with absolute values, is break it into a piecewise function and use the value that, you know, changes the direction from positive to negative. I shouldn't say change the direction, but changes the value of the function from positive to negative as kind of your special number you're going to dance around. So we get 5 for this problem, okay? We have quite a few definite integrals, but I'm only going to give you the main ones. You guys can look in your book for the rest. I'm sorry, quite a few indefinite integrals. So they're basically all the same that you did from definite integrals. They have all the same properties, but without the limits of integration for the most part. So we have k times f of x dx is equal to k times the integral of f of x dx, right? We have the integral of f of x plus or minus g of x dx. Well, that's the integral of f of x dx plus or minus the integral of g of x dx. We have the integral of k dx, and that's just equal to kx plus c. So whenever you're integrating a constant, it's just that constant times x or t or whatever variable you're working with. I'm not adding plus c to these because I actually haven't integrated. I just rewrote the integral in these. This one's saying that you can actually integrate this. You also have the integral of x to the n dx. Well, you guys know that's x to the n, to the power, x to the power of n plus 1 divided by n plus 1 plus c. You guys know that we have the integral of 1 over x dx. Well, this is just the natural log of the absolute value of x plus c. We have the integral of e to the x, which is a really nice one because the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus c. We have the integral of a to the x dx. Well, the derivative of this multiplies by ln of a. So the antiderivative of this is going to be a to the x divided by the ln of a plus c. Then we have all of our trig. We know that sine x dx is going to be worth negative cosine x, negative cosine x plus c. We have the integral of cosine x dx is equal to sine x plus c. And again, if you ever want to double check, take the derivative of this. What's the derivative of sine? Cosine, right? What's the derivative of a constant? 0. So this works fine, right? So you can always check whatever you say the antiderivative is by taking the derivative of it and seeing if you get back to where you started. We have the antiderivative of secant squared x dx is equal to tan x plus c. We have the antiderivative of cosecant squared x dx. This should be cotan, negative cotan, cotan x plus c. We have the antiderivative of secant x tan x dx is equal to, let's see here, secant x plus c. And of course, we have cosecant x cotan x dx is equal to cosecant, should be negative cosecant x plus c. And then the last two kind of special cases that I asked you guys to memorize for derivatives, dx over the square root of 1 minus x squared. We know that this is the arc sine or sine inverse of x plus c for x squared less than 1. Let's see here, we have the integral of dx over 1 plus x squared equals arctan of x plus c, and this is the base case, right? If there's anything else, you're going to have to use something called U substitution that we'll do in a different section, but this is kind of the base for this. All right, so these are kind of our core formulas. There's a few more, but this is kind of our core. And let me see if I have another example for you guys to do. I think that's going to be it. I believe that I covered a lot of antiderivatives in 4.9 or whatever book you're using, the section on antiderivatives. So now do all of those problems using your new notation. So just practice using this notation in the homework. You actually could have probably done the homework without even reading this or watching this video, but I just wanted to add a few things about, you know, trig functions and things like the absolute value and displacement and stuff. We'll go over some more. The next section will be much harder on the substitution rule and U substitution. That section I'll probably spend a good hour on. That's a very important section. That's one of the ones that I'm going to test you heavily on the exam. Okay, so I think that's going to do it. I just wanted to send you guys out a quick video for 5.4, even though you kind of already know how to do it. I just wanted to follow it up with this video. All right, that'll do it.